sharing yangu again now.
Not
Yes.
yet.
Yakuoneka handiti?
Yeah, iri kuoneka but tenda kumiswa interface ke vanhu vari pa.
Pane vanhu vari kubva vasharewo futi.
Yeah, it's now.
Yakuoneka.
All right. Apology, ndandamboita visit. I am now back. So we were saying, we have said, when we have a video can only be stored in a computer if it is digitized, put to base 2. An audio should be put in base 2. What are we saying? We are saying when we are receiving colors from an image, they come into the computer in the forms of numbers. When we are receiving audios, they come into the computer in the form of numbers. When we are receiving videos, they come into the computer in the form of numbers. When we are receiving text, they all come into the computer in the form of numbers. Now we convert all those numbers. When we convert all those numbers, we put them into base 2. When we put them into base 2, then we store. So look at how each number is going to be stored. Each number or letter, when we are talking about a SCII, the normal text, each number or text is going to be 8 bits. 5 is going to be stored in the form of 8 bits. A is going to be stored in the form of 8 bits, a 8-bit pattern of 1s and 0s. C is going to be stored in the form of 8-bit patterns of 1s and 0s. So you can imagine when we are storing a file of an image, each pixel should have either 8 or 24 bits, 8, 16, 24 or 32 bits to represent colors. So you can imagine how big a file is. Now, how do we make files smaller? This is the process of compression. We want to make files smaller because each and every pixel is 8 bits, and a picture, each single picture, if it has 1000 bits by 8, you can imagine how large a single image can be. Worse still, if we talk of a video. Then if we talk of novels and textbooks, if we are saying in a textbook, each letter has 8 bits. Remember, a letter in a computer is a word. It's 8 bits. It's an 8-bit pattern of 0s and 1s. So you can imagine how big a book is. And you can imagine empty spaces after between each and every word. It's 8 bits. So you can imagine how many empty spaces are in a novel and how much storage do they need. You will find that a file will be very big. And how do we make the files smaller? This is what we mean by compression. So this is the topic of the day. So compression basically reduces what is called redundancy. Data that has been repeated. Redundancy means data that has been repeated or data that is not necessary. For your own information, there are several colors in a computer. A computer can produce more than close to 1 million of colors, but a human being can see less than 200 colors in any moment. So every picture that we see very little from a picture. So it actually means you can imagine the amount of data that we need to throw away when we are making a picture for us to make the file smaller. So look at redundancy. So we are saying when we have a file, whether it is a text file, an image, or an audio, we have what is called redundancy. Information that is repeated unnecessarily or information that we cannot perceive. Because a human being sees 10% of the light in the real world. So it actually means most of the colors and lights, we don't need them in a file. We need to eliminate them because we know that eyes will never see them. But there are so many. So it actually means what we see in the real world is less than 10% of what is existing. Otherwise, if you were seeing everything, you could see the COVID viruses that are moving around you, flu and everything, and you run away. But we see very little in the real world, sufficient for us to understand the world. So files, if they keep all that information, they will be very large. So how do we reduce? We reduce file sizes by eliminating redundancy, repeated information, and information that we cannot see. Repeated information and information that we cannot hear. Repeated information and information that we cannot understand. Now, what is temporal redundancy? For you, as a computer scientist, you must understand that there is no video that you see in your computer. There is no moving picture. When you are seeing a video, it means the computer is using a camera to throw 30 pictures per second on the screen. And all the 30 pictures that are thrown on the screen are still images. The computer is throwing 30 picture frames on the screen. And then you have an illusion. You have the false image that there is a human being who is walking. Yet the computer is throwing images at a fast rate, throwing them and removing them. So what do we mean by temporal data? We are simply saying, if a computer is throwing 30 images per second of the same person who is standing on the computer, why don't we fix the camera and then we remain with one image, which remains still on the computer? So it actually means that if you are working on a computer, what are working are the legs. Your stomach is not working and your head is not working. It actually means a video should be able to keep the same stomach and the same head on the computer. Then working is being simulated by legs. It actually means on those 30 frames that must be thrown per second, we are re-throwing legs and hands because they are the ones that are moving. Otherwise, the stomach and the head, we keep the same stomach and the same head on the screen. We don't re-throw the stomach 30 times. This is what is called temporal redundancy. We are looking at the picture frames that are being thrown on the screen, and then we throw differences only, but elements that are similar will remain fixed. So you can imagine the amount of calculations that are being done for us to throw successive image on the computer. This is what we call temporal redundancy. If a person is working on the face of the computer, we keep parts that are fixed, that are not working. We keep them there. We don't throw them back each time we throw a new picture frame. So the computer is analyzing to say, what is the difference between the previous picture frame with the new picture frame? And then when it analyzes, it throws only new information. The information that is remaining static, that is not changing from the previous frame to the new frame. We don't change it. So as the human being is moving, we are changing only legs. We are not changing the stomach. We are not changing the shirt. This is temporal redundancy. Keeping re-throwing differences between successive images on the screen and not throwing the full image. When I am teaching like this and my image is being thrown onto you, we can only re-throw the mouth and the sound. But we don't re-bring the table, the desk, because the desk is fixed. So the desk is thrown once, and we are now re-throwing the hands and the voice. And therefore, our file becomes smaller. So we are selecting differences between the successive images that we are throwing on a screen, because we've said in a video, we are throwing fixed images 30 times in a second on the screen. So how do we re-throw in an economic way? We analyze the previous image and we say, these lights are already there on the screen. So the light that is there on the screen, we don't need to rub it and re-throw it again. We simply leave it there. We are now throwing the lights that are not existing at the moment. So we are analyzing the differences between successive images, and then we throw different images after every millisecond. This is what we call temporal redundancy, eliminating what has been thrown by the previous image, and we don't rethrow it on the screen. Then we come out to what we call spatial redundancy in images. Look at what is happening. Let me take this pen. This section that I've drawn on here has similar colors So as these colors are being sent over the wire to you, it doesn't make sense to send the same pixels with the same color. We are simply counting the pixels that are blue here. Then we send a single blue pixel. When we send a single blue pixel to you down there, we say, when it reaches your machine, we say multiply the blue pixel by 1000 to produce the other 1000 blue pixels that have remained here. So what you are seeing over the wire, we are simply sending 1 pixel of blue color. Then we are going to multiply it by the number of pixels that have remained here on the other end of the wire. So this is spatial redundancy. We are avoiding sending similar pixels. We simply count to say this pixel, this type of a pixel, how many are they? Then we send one of them. When 1 pixel arrives at the other end, we say times 1000. Then the picture is regenerated. So this is spatial redundancy. We are sending 1 pixel to represent many pixels in an image. Then spectral redundancy. We are trying to see colors that are pertinent and colors that are not pertinent. And then we send colors that have value. Colors that can, when they mix on the other end of the wire, they will regenerate the other colors that did not arrive to the other end of the terminal. Then we use what is called, in colors, we use what is called psychovisual, exploit perceptual properties of human beings. Like I have said, mukaenda munoona mamwe if you go into the world of colors, you will see kuti kune vanonzi ma-X-rays, kune vanonzi whatever. All those are forms of light. What do we see in the real world? We see less than 10% of the light that is in the real world. If we were able to see truly, hapana munhu aimira because waitiza, kana zvinhu zvinoitika in the real world is, if you see truly what is happening, if a person stands before you, you can see what he has eaten, what is in his stomach and everything. So it actually means, right now, if you were seeing truly, you were going to see air particles and so on and so forth. So it actually means there are a lot of things that we can't see. So for those things that we can't see, we need to remove them from files. When we remove them from files, our files become very small. And when our files become small, we can now send them over the network. Right? So this is the same with hearing. We hear a very small percentage of sounds that exist in the real world. And when we hear a small percentage of sounds that exist in the real world, it actually means some of the sounds that we do not hear, it's not necessary to keep them on a file. We should remove inaudible sounds so that our files become smaller. And then we can actually be economic in terms of utilizing the resources that we have. So compression is categorized into two: lossless compression, which is done to code files, software files, text files, and other very important files, where data can be compressed and reconstituted and compressed without loss of detail. These are referred to as a bit preserving or reversible compression. What are we saying? We are saying if we compress a text file, we don't lose any information from that. We keep our information intact, so that when the file reaches the other end, it is going to be reproduced exactly as it is. Now we go to lossy compression. Lossy compression is where we obtain a file which is of poor quality than the file that we originally have. We have lost some information we cannot recover. So for text files, software files, we use zipping or RAR files. We use lossless compression, where we are utilizing a compression method that does not lose any information. But on videos and audio, we do lossy compression, On video, we remove some other colors that are not necessary. We remove some other sounds that are not necessary. We remove some other colors that have been repeated unnecessarily. We remove some other sounds that have been repeated unnecessarily. And then we remain with smaller files. This is what we call by lossy compression. So it actually means if you compress a video or an image or a voice, you will never get the original voice, but you can estimate, you can get very close back to the original file. This is what we mean by lossy compression. So lossy compression is done in videos, is done in audios, because there are sounds that we cannot hear. There are sounds that are unnecessary. Like right now as I speak, the file that is coming to you has sounds of cars that are moving outside, has sounds of maybe flies that are around me, has sounds of maybe the room is reverberating and the sounds are being sent to you. All those are necessary sounds. When we get into a file, we must be able to analyze sounds that are necessary to a file, and then we remove them. Our file still remains useful, but it cannot be an original file that we had in the beginning because some of the information is lost. Now, if an image is compressed, it clearly needs to be uncompressed. So to be compressed is to be coded, to be uncompressed is to be decoded. So before it can be viewed or listened to. So it actually means that when we store an image or when we send an image over the network or a video, right now, as I'm speaking, the video is being compressed on my machine, sent to you. When it arrives on your machine, it is being decompressed. When it is decompressed, you can now consume it. The same way, if I want to send a file on an email, I'll make it a raw file. Then I send it to you. When you want to read the contents of the file, you decompress the file, you unzip the file so that you can see the information. This is exactly what is happening to video and audio as it is coming from my machine to you over the other end of the wire. It is being compressed. When it gets compressed, it is sent over the wire. When it arrives to you, it is going to be decompressed, and then you are able to see it. So when we compress videos and audios and images, we lose some data. This is called lossy compression. But when we compress software files and text files, we don't lose any data. This is called lossless compression. So lossless compression frequently involves some entropy encoding and is based on information theory techniques. What do we mean? We are saying we analyze the characteristics of information because we have said a text file when we are sending a text file, we are sending a stream of zeros and ones to you. So when we send a stream of zeros and ones, we analyze that stream of zeros and ones to say, how can we make it short? If every word is 8 bits, we can emulate to change 8 bits to 3 bits or 4 bits. When we emulate to change 8 bits to 3 or 4 bits, the file becomes smaller. This is what is called entropy encoding. So entropy encoding simply means lossless compression. The compression that is done by analyzing the characteristics of data so that you can make it smaller without losing it. So lossy compression is called source encoding techniques. There are so many of them, and they may involve transform encoding, differential encoding, vector quantization, and a lot of mathematics that is involved. So here, I'm simply going to show you examples of lossy compression, but we are not going to do lossy compression because it is quite mathematical and you crack your heads, you may die. But otherwise, we can do lossless compression because lossless compression is some form of statistics. If you know statistics, we are taking statistics to say, if the file has so many A's, maybe the file has 1,000 A's and 2,000 B's and 2,000 C's, which character is appearing most, which character has the highest probability of appearing? That character should be given only 1 bit. The file is now smaller. If Q is not appearing in most of our language, if it is Shona, we don't use Q much. We say it is only Q which is going to be transferred using 8 bits. But R is always there in Shona. We say R is going to be 1 bit. We no longer need the 8 bits for R. We no longer need a full byte for R. We simply use 1 byte. Because R is so pertinent, we use it in every sentence. We are using the characteristic, the probability of a letter occurring. If the letter has a high probability of occurring in a sentence, we reduce its number of bits so that it becomes very small. So frequently occurring letters will get to 1 bit, 2 bits, 1 bit, 2 bits. So our file is becoming smaller. Letters that are occurring less frequent, those are the ones that will be having a larger bit, 7, 8 bits, 7, 8 bits. So we are making the file smaller than a situation where every letter was 8 bits. So we are working on the statistics of occurrence of each and every letter or word. This is statistical encoding. Entropy coding is statistical measurement of occurrence of every letter or word in a total of a novel. So it actually means before the novel is sent to the other end of the wire, we count kuti vana D vangani, we count kuti vana A vangani, we count kuti vana mother vangani. Then those words that are appearing most, they are given 1 bit. Words that are appearing fairly, they are given 2 bits. Words that are appearing fairly more, they are given 3 bits, and so on and so forth. Words that are infrequently occurring, they are given 7, 8 bits. Then the file becomes very small. So this is just the statistics and probability. Unlike source coding, in source coding, we will do vector quantization, we will do differential encoding, we need a lot of mathematics. So we will just need an appreciation of what we mean by lossy compression. And we understand that lossy compression is done on videos, is done on audios, and is done on images, right? On audios, we analyze the weaknesses of the ear. Then we remove sounds that people do not need. Then we remove sounds that have been repeated several times. On images, that is video and pictures, they are all images. We analyze colors that human beings cannot see, lights that human beings cannot see. We remove them from the file. And colors that have been repeated so several times, we remove them from the file. And the file will never look like the original file because we have thrown away some of the information. But in a text file, we did not remove anything. We have simply worked with the statistics to say, let us send a single A to the other end of the wire. Because we have so many A's. Or let us send all A's, but every A is now 1 bit instead of 1 word. Right? So look at the compression techniques or coding techniques. We call them compression techniques or coding techniques. These entropy techniques, they use statistics. This source coding, they use the physics or mechanics of colors, right? And how we understand colors, how we hear voices, and how we can interpret them, right? So look, we have transform coding, we have differential coding, which can be divided into DPCM, DM, and ADPCM. Here we have FFT, then we have DST, which are discrete cosine transform and whatever. Then here we have vector quantization and so on and so forth. These are examples of, so here we are talking about, this is where we talk about videos. Here, this is where we talk about videos, audios, and images. Here, we are now talking of mostly text files, but we can still also do images. Look at statistical encoding. We are looking at the probability of a letter occurring. If the letter occurs so much in a page, we need to give it 1 byte. If a letter is infrequent, it doesn't occur much, we can give it 7 bytes. Here, we don't do any statistics. We are simply eliminating repetition. To say if A has been repeated 10 times, we simply say A times 10 than to write A. We simply say A times 10. So here, you just need to appreciate. You just need to appreciate what. Oh, people. Some of you are making a bit of. So here we just need to appreciate. But here, this is what we are going to do. We are going to do this one. We are going to do this one. We are going to do this one. Those are the three compression mechanisms we have. But you are seeing an array of compression methods that we have that we are going to eliminate. But I'm simply making you appreciate what we mean by compression and what we should be doing in compression. So this is the realm of entropy coding and source coding. So make sure that you understand run length coding, you understand Shannon funnel, and you have a bit of some Huffman coding. You will be okay. We don't do everything, right? So there we are, lossless compression. We've started with repetitive sequence suppression. Look, repetitive sequence suppression. This is the area that we are talking about, repetitive sequence suppression, right? So there, look at what is happening. This is simple repetition, which we can avoid. Look at this statement here. These zeros. From here, each zero was going to be 8 bytes. And we have 32 zeros. Instead of writing this, if we convert this to base 2, it actually means we were going to have 32 times. We were going to have 32 times 8 bytes. Now look at the statement that we are going to transfer. We cannot compress 8 because 8 is a single value. We cannot compress 9. We are going to take 9 as it is because it is a single value. We cannot compress 4 because 4 is a single value. So we have taken how many bits? 8, 16, 24 bits. 24 bits. When we have taken these 24 bits, look, here we are now having another 24 bits for F32. 32 is trying to indicate that we are sending 32 zeros. And the F is a signal for 0. And then how many zeros are we going to send? 32. So this is the statement that we are going to store or send over the network. Instead of sending this large number, we have suppressed 8 times 32 bits, right? 8 times 32 bits has been replaced by these 24 bits. And when we have replaced these 24 bits, we are now sending this small signal to the end of the wire, or we are now storing that on a disk. It becomes cheaper. So we are suppressing repeated figures using a flag, which is an F, and then we write the number of times, which is 32, and then we are done. So compression savings depending on the content of data. So you can imagine if we are writing a composition, this kind of compression does not work much because we don't find so many zeros like this in a composition or in a novel. So this kind of lossless compression doesn't work. Maybe it works in compressing empty gaps between words because empty gaps are similar. So applications of this, we do this in bitmaps, in pictures, because a picture will have thousands of black images, black pixels, thousands of white pixels. This is where we use this kind of thing. We suppress repetition. If we have 500 black pixels on a single image, we simply have one pixel and then a signal to show that there were 1,000 of them, and then we can send it or we can store it, so that when the person who wants to read the data is now reading it, we simply send 1 pixel and it is multiplied by 1,000. So blanks in text can be done like that. Backgrounds in images can be done like that. This is how we suppress them, and they become very small files. Then now we can talk of run length coding. This encoding method is frequently applied to images, right? It is a small compression component used in JPEG. In this instance, sequences of image elements or pixels can be reduced in such a way that pixel colors that are appearing more should take a smaller number of bits. Instead of saying each and every color is 8 bits, we can turn other colors to 2 bits, other colors to 4 bits, other colors to 6 bits, and then our image becomes smaller. Look at what is happening here. Instead of sending 1, 2, 3, 4 by 8 bits, we are simply sending a 1 and we are indicating that there are 4 ones. This one taking a 8 bits and this one taking a 8 bits, and it actually means we have sent 16 bits instead of what? 8, 16, 24, 32. Instead of sending 32 bits, we have simply sent 16. Here, 1, 2, 3, 4, 5, 6 by 8 bits. We were supposed to send 48 bits. Now we are still sending 8, which is almost 16. So this is how we are compressing the file. Nala? I wait for security officer wanosvika. So look at what is happening. We have compressed this long number. We have compressed this long number by doing what we've done there. We are simply sending 4 bits. We are simply sending 8 bits per each signal that we have instead of repeating it. This is repetition suppression. Then we come to lossless algorithm. This is a simple form of statistical. We are saying lossless is a statistical encoding. We are doing pattern substitution. Why are we saying it's called pattern substitution? Because we have said every file that we send online is a series of patterns, zeros and ones, to mean that your novel is a pattern of zeros and ones, and we are observing the patterns to say, can these patterns be repeated? Can these patterns be shortened so that we send it or we store it in a more economic way? This is simply statistical encoding. Here, the substitute of a frequency, here we substitute a frequently repeating pattern with a code. The code is shorter than the pattern, giving us compression. The simple pattern substitution scheme could employ predefined codes. For example, replace all occurrence of the word "the" in a novel. We know that the word "the" is always occurring. So we can find it as 1, 2, 3, "the" has 8 bits times 3, which is 24 bits. So we can simply find a token like this one to represent 24 bits. Now we have that end, and that end has 8 bits. We can still reduce that end to 3 or 4 bits. Instead of having 24, we now have 8. Then we seek to reduce that 8 to represent this word. And then for 24 bits, it is possible for us to have 3 or 2 bits for every word that has 24 bits. And that pattern becomes very economic when we are now storing the whole novel or the whole Bible. So more typically, tokens are assigned according to frequency of occurrence of patterns. You count the occurrence of tokens, you sort the tokens in descending order. Kureva kuti Bible rako iwewe risati ratumirwa on the network, tinotorikaunda all the words, that is compression. Toti vana the i10,000, vana is i5,000, vana mother i2,000. We create a complex. We create a complex table which shows the probability of occurrence of each and every letter. Then we encode them. We are now converting into bit patterns. So we assign some symbols to the highest counting tokens. A predefined symbol table may be used. Then that table is now sent to the other end of the wire, which will then be decompressed. And when it is decompressed, when it is decompressed, you can now begin to actually see the document. So it actually means as the document is being sent to you, it is now a complex assortment of tokens, which is now more economic when compared to the actual file that we would have if we actually send the original file. The original file will be very big, but now we have a small file, which is an intelligently organized assortment of tokens, which would then be reorganized when they reach the other end. Right? So lossless compression, we said it uses entropy encoding. It studies characteristics of the document. Then when it studies characteristics of the document, it recognizes the document as a series of patterns. And then it takes patterns that are repeating so much in a way that they become smaller. And patterns that are less frequent, they become a bit bigger. And then each and every pattern becomes unique, and it can be replicated when it reaches the other end of the wire. Now look at the sample that we are giving here. Look at this. We are saying we are reading a page, and we've seen that on a page we have 15, ma A aripo 15, ma B aripo 7, ma C aripo E6, ma D aripo E6, ma E5. This is a page. Now look at what is going to happen. Look, assuming that A was going to have 8 bits by 15. You can imagine how many 8 bits were we going to send. B was going to have 8 bits by 7. How many bits were we going to send? C was going to have 8 bits by 6. How many bits are we sending? D was going to have 8 bits by 6. How many bits are we sending? E was going to have 8 bits by 5. Then you calculate the total number of bits. Now, if we calculate using our probabilities of occurrence, we are realizing that A now is more frequent, followed by B, followed by C, followed by D, followed by E. Now look at what is going to happen. A is going to have 2 bits 0, 0. For every A, we are going to send 2 bits. So if we had 15 A's by 8, what were we going to have? We were going to have, let me calculate here. We were going to have 15 by 8. What were we going to have? We were going to have 15 by 8. We were going to have 120 bits. Now, on the 120 bits, we are now going to send 2 bits by 15. We are now going to send only 30 bits for A. Then for B, instead of it having 8 bits, B is now 0, 1. For B, we now have 2 bits. So it actually means B times, how many B's do we have? We have 7. So we are going to have 14 bits for 7 instead of 7 by 8, which was 56 bits. So we are going to send 14 bits for 7 instead of 56 bits. Then for C, we are going to send what? For C, C is going to be 0, 1. We are going to send 2 bits for C. 2 bits by how many? By 6. Then for D, D is going to be 0, 1, 1. For D, we are now sending 3 bits, right? For E, we are going to have 1, 1, 1, right? So for Shannon-Fano coding, A is 2 bits, B is 2 bits, C is 2 bits, D is 3 bits, and E is 3 bits. You can imagine how small our file is now. So we are going also to use this same technique to do Huffman coding. Look at the tree for Huffman coding. The tree for Huffman coding, A was going to have 1, 0. So A is now 1 bit. Then B 0, 0, 1. 0, 0, 1. That's B. C was going to be 1, 0, 1. That's 1, 0, 1. That's C. Then D was going to be 0, 1, 1. D was going to be 0, 1, 1. Then E was going to be 1, 1, 1. So you can see A is now 1 bit, B 3 bits, C 3 bits, D 3 bits, E 4 bits. This is what we were going to have if we were going to use a Shannon-Fano coding. So it actually means for every letter where we were going to send a full byte, we are now sending a single bit. And then it becomes very economic. So this is encoding. And do you see that when we are encoding, all our letters are already in base 2. When they are in base 2, they are also very small and very efficient to send. Right? So these are examples of coding techniques that we can use. So you are seeing that everything has been converted to base 2, and each letter that is occurring very frequent is now being shortened to a very small value. And therefore, the value that we are storing are very small. So that process, what are we saying? We are saying in the sending machine, we compress by creating a table of statistics of patterns. Patterns that are occurring more are going to have very small bits. Patterns that are infrequent are going to have fairly larger bits. And then when we send the table of frequencies to the receiver. That same table of frequencies is sent to the receiver. Then it is going to be used by the receiver to reconstruct the file. And when you reconstruct the file, you can now utilize the file as the reader of a file. Ladies and gentlemen, this is the summary of lossy compression. Do you have questions? Can you ask questions then? Yes, Peter, you can speak.
Can see you.
You took your binary digits, took them from the leaves.
Hello?
When you took your binary digits,
Yeah.
you started from the leaves.
Yes, you start from below.
Okay, you don't
start from the top.
You don't start from the you don't start from the top, you start from below.
Okay. Okay, thank you.
Hello, Farai.
On the same token of question Peter asked, I suppose I start from the top. Will it be the same in terms of the byte arrangement, the bits arrangement at the as a resultant?
Bits can be arranged differently, but still you will not have two letters having the same. The idea is you will not have two letters having the same pattern. To say A is 110, B is 110. You should not have that scenario. If you have that scenario, it means you have worked it out. You have worked out wrongly.
Oh, okay. So it means each individual character must not be, have the same kind of bits.
It might have the same kind of, it can have the same number of bits, but the bit patterns, to say if A is 110, it means on the list there is no other letter which is going to have 110.
Oh, okay. All right. I understand now.
That's the idea.
Okay.
Any other question? All right, let me stop sharing here and then I share something on what do we call this one? On images and videos. All right.
It doesn't matter what you are talking about. You can start from the top.
Right, I want to share this file with you here. Oh, okay. I'm sharing the one which I didn't want to share. Let me share again. Oh, I'm not seeing. Yes, this one. Are you seeing the file that I've shared there?
Why don't you saying image compression?
Image compression.
Yes.
Yes.
If I move it like this, do you still see?
Yeah.
Yes, sure.
All right. Right. So look at what happens. When we were talking about lossless compression, we were talking about files that do not need to lose their quality, like text files, like code files and everything. That's where we use lossless compression. Now, when we are talking about images, when we are talking about images, when we are talking about videos, we can say our eyes and ears cannot distinguish some of the colors. So in such a situation, we can use lossy compression methods. We can remove colors that we cannot see. We can remove voices that we cannot hear. For example, as I'm talking right now, maybe my phone is ringing and you are not hearing it, but the mic is, the speaker is capturing that, or whatever a voice capturing item that is capturing even the phone which is ringing. Now, if we get into an audio authoring tool, we can see that there is unnecessary sound which we can actually remove to make our file smaller. Just like we are saying, a computer can make millions of colors. And some of the colors that exist, they are very bright and they can take so many pixels, but human eyes cannot see them. So what should we do? We should be able to remove such colors because they are not necessary. So these methods are cheaper. They take less time and space when it comes to sending millions of bits per second because we eliminate a lot of data that we actually do not need. So several methods have been developed using loss compression techniques like the JPEG, then we have the MPEG, we have for videos, we now have MP3 videos and audios, we now have MP3, MP4, and so on and so forth. All those things, on those compression methods, they utilize the fact that we don't hear all sounds that exist. We don't see all colors. So that which we don't see, that which we don't hear, is not very necessary. We utilize the weaknesses of the eyes and the weaknesses of the ears to remove sounds that we cannot hear and remove colors that we cannot see from pictures and videos. So an image can be compressed by a two-dimensional array of a table of pixels, that is picture elements. A pixel is the smallest unit of an image that we can actually store on a computer. So we break an image into an array of pixels, and then we deal with each and every pixel, right? A resolution can be used for compression purposes. If we change each pixel from 8 pixels to 24 pixels, we have increased the number of colors and we have increased the size of file. So if we change our image from 24 pixels, from 24 bytes per pixel, from 24 bits per pixel to 8 bits per pixel, we are already compressing because we are reducing the quality of the image.
There's neural super assignment here.
So when we reduce from 32 to 24 to 8, we are reducing the number of bits per pixel. It actually means we are compressing because we are reducing the quality of the image and we are making the pixels smaller. Right? So in JPEG, grayscale picture is divided into blocks of 8 by 8 blocks to decrease the number of calculations and so on and so forth. This is now the technique that we are using. We are saying per each pixel, if we can look at the per each group of pixels, if we can look at colors that we can still eliminate. A single pixel does not matter, but the relationship between two pixels will determine the eventual color that will get into the eye of a beholder. And therefore, we need to look at spatial redundancy, and then we remove some of the colors and some of the pixels that are not necessary. So in video compression, the method is used to compress a video, which is the MPEG. In principle, motion picture is a rapid sequence of a set of frames in which each frame is a picture. Like I've said to say, when you are doing compression, you always imagine a video as a series of still images. There is no moving image in computing. Every image is a still image. But what makes the sense of moving is because we are throwing 24 images per second, and the human eye is very weak. We tend to think that there is a moving person on the screen of a computer. There's nothing like that, or on the screen of a TV. No person will ever move. Now, how do we compress a video? We are using the concept that a video is a series of pictures. So we compress each and every picture. This is the spatial redundancy. And then we eliminate we eliminate similarities between successive pictures. That is now temporal redundancy. So it actually means that in a video, we use techniques of pictures, then we use techniques of successive pictures. That is a moving picture, a still image from point A to point B. How far has it changed? If it has not changed, we don't recalculate the colors. Therefore, so in video compression, we talk of temporal redundancy, eliminating similarities between two successive still images in a video. Then we talk about spatial redundancy, working with a single image, compressing a single image. Then temporal redundancy, we are combining two images as they walk on the screen to say, what should we eliminate from picture A to picture B? There are things that the eye will never discover. So let us remove them. So in other words, a frame is a spatial combination of pixels. So when we are compressing a frame in any video, we are doing image compression, spatial redundancy in a single image in a video. But when we are showing, when we are compressing the relationship between the previous image and the next in a video, we are now doing what is called temporal redundancy. So we have combined the spatial redundancy and temporal redundancy to come up with a smaller video. So compressing video means spatially compressing each image and temporally compressing a set of frames or a set of pictures that have been combined to lie to you that a human being is working. So if a video is a mammoth liar. Look at what is happening. So these are pictures which are being thrown on the screen. So as we move from the last picture to the first picture, checking similarities, we are doing what is called temporal. We are removing temporal redundancy. We are removing temporal redundancy from the file. But when we are now analyzing a single picture in that set of pictures, we are now doing spatial redundancy. We are removing spatial redundancy. So a video is a combination of temporal redundancy and spatial redundancy. But a picture, we do spatial redundancy. Right? So let us talk about the audio. So audio compression can be used in speech or music. For speech, we need to compress at 64 kilohertz a digitized signal, while for music, we need around 1.44 megahertz signal. So the two categories of techniques used in audio compression are predictive encoding and perceptual encoding, right? Maybe predictive coding, it analyzes the difference between samples, right? Like we're doing in an image, in a video, to say we analyze differences between successive images. Here we are analyzing differences between successive samples of the audio sound. Then perceptual is the most common technique which is used in encoding MPEG-3. We are also removing sounds that we cannot see, that we cannot hear. Sounds that are not necessary, sounds that we cannot hear, sounds that have been repeated can also be removed from a file. So ladies and gentlemen, I have simply given you a summary of these coding techniques. I did not go into detail. So it is you who is going to practice, but I wanted you to get the general image of what we mean by compression. This is what we mean by compression. We divide it into entropy encoding, that is statistical methods for text, then into source coding, that is the methods that are suitable for audio, video, and images. So the only difference is that entropy is lossless, then source coding is lossy compression. Lossy compression reduces quality. We cannot recover the original file. Right? Then with lossless compression, it maintains the quality. We can recover the original file, but it doesn't reduce size as much as lossy compression.
After lunch.
So any questions, ladies and gentlemen? Let me listen to questions from you. Let me stop sharing there and hear from you.
Oh, okay. All right, it's okay.
Do you have questions? I'm not
Yes,
seeing
I do
any.
have one.
All right. It's okay.
My question is, at some point I lost the network along the way, but I could not understand. I could not understand where you were talking about the formatting in the Shannon coding. My question is, do we start on the Shannon fun coding? We start from it's Huffman coding. It's bottom up.
Hello?
May you correct me this?
Huffman coding.
Hello?
Yeah, I'm hearing you. I'm saying on Huffman coding. Let me come back again. Right. Let me share this. Are you seeing my screen there?
Yeah, now I'm seeing it.
Right. Look at the probabilities there. A has 17 characters, B has 12, C has 12, D has 27, E has 32. So where did we start? We started from B and
I think
C.
we start with the one with the biggest number.
You start with one with the biggest number. Which one is that one?
Basically, I thought it's A. That has got 27.
Now
Number of recurrence.
look at what has happened here. We have started with B and C with the smallest numbers. Have you seen? Are you seeing it? Because we are starting from the bottom. The method that has been used here is starting from the bottom.
Okay.
We have started with B and C with the smallest numbers. So we have added 12 and 12 to come up with 24. Then we have said now, now we have gone to say which one is the next higher number. A, look at how we have used now. Now we are saying A, we are now saying 24 plus 17, which will give us 41. Look at now our new tree with the A. Are you seeing our new tree with the A there?
Yes.
Then we have gone on to say, now we are left with what? With D and E. Look at the way we have combined D and E there. We have combined our D and E, which is D, which is 27, and E, which is 32. Now 27 plus 32, which gives us 59. And then look at the way we've combined them here and the way we've gone to make the final tree. Are you seeing it?
Yes.
So by saying starting from the bottom, I was trying to say we are starting from the least probability, those letters with the least probability. And eventually you will see that the letters with the least probability are the ones which are going to have the longest chords. Are you getting it?
Yes, I got it.
Now, so look at the final tree. Look at the final tree there, which is now, look, D and E with the highest probability. D is 0, 1. Do you see that? It's 1, 0, I mean. Okay, we are counting from, it's 1, 0. Then we have started from the bottom as we create our tree. But when we are reading, we are now starting from D is 1, 0. Then E is 1, 1. A, 0, 0. B, 0, 1, 0. Then C, 0, 1, 1. So in other words, we have started from the beginning as we create our tree. But when we get through with our tree, we read our values from the top going down.
Okay.
Did you get the sense?
Very clear.
Yes. Any other question? Let me check. It seems we no longer have a question there. Ladies and gentlemen, this is what I wanted to talk to you about. I don't have anything much. If you don't have questions, now this is my last lesson with you, the third lecture. If you have other questions, you are going to throw your questions on our group. But I might not be answering your questions very fast because from today onwards, I will be on leave. So I might not be attending to you regularly up until you write. So this is the last time you are going to be seeing me responding to you fast enough. Maybe starting from Monday, if you ask me a question, you will see me answering after 3 days or 4, because I will not be in office. Yes, Peter, you can ask.
Okay, on the LZW logarithm.
Huh?
So what I want to ask something on the LZW logarithm. When we encode and we get our values encoded, what do we do next? Do we change those values into binary? The encoded values.
Everything that we have on a computer is always in binary. Do you know that? Do you know that your computer does not know anything except 1 and 0?
Yes, that's correct.
Yes. So think of everything that is in your computer as a series of patterns of 1s and 0s. That's only what a computer can have for you.
Okay. Then my question continues to say, suppose I get a 1, 2, 3 as the coded figures. Am I supposed to represent the 1 in ASCII when we use 8 digits a number? How many digits am I going to use, say, to represent 1 in the binary?
Have you seen kuti coding coding algorithms atati chishandisa apa ari kutry kuita avoid 8 bits per letter?
Correct.
Yes, this is compression. We are saying computer scientists have realized that keeping 8 bits every time is wastage of space and memory, because we can have a situation where some other letters can have 1 bit, some other letters can have 5 bits, some other letters can have 3 bits, and by doing so we are becoming economic. Answered or not?
Thank you.
Shelton.
So my question is a practical question. Like sometimes maybe we have a text file. The text file is very big. Maybe it's more than 1 gig. Then we want to compress it into a small file. Then sometimes we use WinRAR to compress files so that it's going to be a small file. What type of compression is that?
It's lossless compression.
Oh, okay.
Or entropy, because when we are compressing text files, we want all the letters when we are recovering the file.
Okay. All right, I answered.
Okay. Then Clemens, is your hand up? If Clemens' hand is not up, let us hear from Farai.
Thank you, sir. I've got a scenario again on the LZW algorithm. How do I encode, say, C, D, and E? Because A can be given 0, B can be given 1. What about C, D, and E?
What are you trying to say?
Like, for example, when I've got a compressed output like A, B, then 2C, 1D, or 8E. How am I going to encode the 2C or the 1D in my compressed output?
We are talking about LZW.
Yeah, sure.
LZW works with what? With a mirror and it.
Yeah.
In LZW, we are looking for similarities.
Okay.
Yes. Yes.
We read the first in LZW. We say what we have read so far. Is what we want to read. Is there anything similar between what we want to read and what we have read so far? If there's something similar, we say we've already read this, we don't know, we no longer need to read it again. So the process itself ukatarisa zvakaita mutextbook menyu ka iri kukuratidzai how to find the similarities between text, haisi kuzonokushowai on how to code the actual how to store the actual result.
Yeah, sure.
Are you seeing it? So your focus on LZW is to understand how you find similarities between text that has passed the window and text that has not yet passed through the window.
Yes, yes.
Now the process of going to store for encoding is another one which is going to take place. But how do we get new? How do we encode? We are simply encoding in LZW. We are simply creating a dictionary of what we've read, and we are finding similarities to what we've not yet read. And then we can simply say these things are similar. Let us make them one.
Oh, okay.
Saka, in your textbook, in your module, it doesn't show you how you are going to finally store that in bits.
Yes, sure. That's our problem.
So you must be worried about how you are simply comparing figures, how you are reading and making your compression. Then when you read and make your compression through the sliding window, you have not yet gone to do the binary encoding and the storage.
Okay.
Another question, if it is there. Right, kana tisisina ma questions, ladies and gentlemen. You can note the following. Please go and understand what you were writing in your assignments. Power.
Yes, sir.
Yes. When you understand what you were writing in your assignments, maybe for compression this time, you may need to worry much about Shannon Fano, run length, and Huffman coding. Then you also need to understand how you also need to understand how the MP3 works. Then
Run length.
So we've said you need to understand your assignments very much, and then you need to understand the compression methods. You need to understand Shannon Fano, run length, and then how the MP3 works. And the MP3, right? Then other items that are very pertinent. You need to understand sampling in detail, how sampling occurs, and quantization is the process of what? Analog to digital conversion. You know that. And to use suitable diagram to explain that. Then characteristics of multimedia. Then components of the video system. Then the difference between component video and composite video. Then HDTV. Then different video connectors. Then components of multimedia. Then RAID levels. Farah, you still have a question?
No, sir.
All right. So we no longer have questions, and Watatondera, do you have a question?
No, sir. No, sir. I don't have. I think it's clear.
So, ladies and gentlemen, I will not be responding too much. I'm going on leave until you write. So please read and prepare for your examinations. I won't see you regularly. This is my last lecture with you. I don't expect to meet you again. Clemens, do you have a question?
Yes, sir. Can you hear me?
Yeah.
Okay. We just want to humbly request for the slides you've been using for presentation.
Yeah.
Okay, thank you.
All right, it's fine. Thank you, ladies and gentlemen. So let us meet in the examination when we write.
Thank you, sir.
Thank you, sir.